Could you see?
Yeah, I see it.
Okay, good. So we are trying to figure out the electric field at a point P at a distance Z along the Z axis of a shell of radius R that has a surface charge density sigma. Okay, so we already said due to symmetry, the only component for the electric field that will survive is that with the Z axis, is in the Z direction. Okay, so the way we could do this question is we can take a patch, yeah, we could take a small slice on the surface of the sphere, okay, connect it here to this. Of course, this is on the surface of the sphere, so this would be an R. There is nothing in the middle. In the middle, this is a shell, and this angle here is theta, okay, and we can connect this to our observation point. So this is our source, right? So this will be our separation vector. And let's say that this angle here is phi. No, let me not call it phi because I have to use phi for spherical coordinates. Yeah. So if I were to project this here, this here will be phi. So let me call this angle here alpha. Okay. Okay. So now we know what's Coulomb's law that governs this electric field. Do you know the formula? Yeah.
In this case, it would just basically be for the field, it's just the charge.
It's ER, right, is equal to 1 over 4 pi epsilon integral along the surface of sigma as a function of the primed coordinates r prime over separation vector square in the direction of the unit separation vector dA prime. This is Coulomb's law for a surface charge, sigma. Got it? Okay, so now what I'm interested in is so basically I need to figure out what my dq is. First, let's find what this guy is. So the separation vector from the diagram, law of cosines. Remember law of cosines? It's this distance here is z. So because this is the z-axis. So this is z squared plus r squared minus 2 rz, right? Cosine theta. Already? Okay, now what we have to do next is if you were to take the surface charge density, yeah, I'm basically interested in sigma dA, right, or sigma dA prime. Okay, what is this? Well, this is a uniform surface charge density. And what's dA prime? If you studied chapter 1 in Griffith, you'll find out that dA prime is just dl r dl theta dl phi. You remember?
Right.
Now this is a shell, which means dlr is just r. It's the radius of the shell. Dl theta in spherical coordinates, if you remember, yeah, it's r d theta, right? And theta goes from 0 to pi. We'll do the integral at the end. So let's just leave it as is now. And what is dl phi? dl phi, if you remember, is r sine theta, because phi changes, yeah, d phi. So this is sigma dA prime. Right, which I will plug into Coulomb's law. Now, except that the electric field will have a z component, and the z component will be what? Now notice, in order to make a right triangle here, I need to project this at 90 degrees. Yeah, and if I do that, then cosine alpha, because cosine alpha will pick up the z component of my electric field, right? Because my electric field will be like this, and I am interested in this component. Oops, I shouldn't do it in red, because I'm interested in this component here. So it will be whatever the electric field is times cosine alpha. So I need my cosine alpha in terms of the variables of the problem. So as you can see from the figure, yeah, if this is r, this here is 90 degrees. So this guy here will be r cosine theta, and the entire distance from here to here is z. Yeah, so if I subtract z minus r cosine theta, I would get this piece here in my triangle. Yeah, this would be z minus r cosine theta. Z minus r cosine theta. So now cosine alpha is z minus r cosine theta over the separation vector. Right? And the separation vector, we've already wrote what it is. We have it. Okay, so now we can go to Coulomb's law. So the electric field, so is this okay, so my electric field will be 1 over 4 pi epsilon, right? Put everything together now. So sigma dA prime is just sigma r squared. Wait, no, I have how many r's do I have? I'm supposed to get sigma r d theta r sigma r squared. Why do I have an extra r? dl theta. Oh yeah, there's no r. I doubled one of the r's. So this is just sigma, right? Yeah. So then sigma r squared sine theta d theta d phi over separation vector square times cosine alpha to pick up the z component, and that's all in the z. So this is my electric field. Okay, so now let's go ahead and get into that mathematics, right? Now let's simplify this a little bit. Now I know that phi is going a complete circle, so this guy here will just get me a 2 pi. Yeah, because you're going from 0 to 2 pi and there's no phi dependence in this. D phi will just get you 2 pi. So then E will be 1 over 4 pi epsilon right? R squared can come out, sigma can come out, everything constant can come out. I have a 2 pi, and I have z. So cosine alpha we said is z minus r cosine theta. And this is, by the way, this is, I don't know why I wrote small r. We're only on the surface of the shell, so it's always big R. So big R, right? Over separation vector, and then I have separation vector squared, so this becomes separation vector cube. So that's just z squared plus r squared minus 2 rz cosine theta, right? All raised to the 3/2. And what else do I have? A sine multiplied by sine theta d theta. Right? Okay, so now it's a matter of evaluating the, oh, and by the way, theta goes from 0 to pi. Yeah? Okay, so we could use substitution to because you know, for cosine, because sine is there. So if we let u to be cosine theta, then du will be minus sine theta d theta. Okay, I'll come back to the constants. I just want to evaluate the integral now, so I'm going to take this part alone. Okay, and so now let's change the bounds. So if u is 0, or if theta is 0, u is 1, and if theta is pi, u is minus 1. So then we go from minus 1 to 1 on the integral. Z minus r u times, or actually I'm going, so okay, so what I did is I have a minus du, and I have it going from 1 to minus 1, so I will flip the bounds at a cost of a minus sign. Okay, so I don't have to put the minus sign for the du. So du over z squared plus r squared. Remember, z and r are constants here. 2rzu. And this is raised to the 3/2. Right? Let's see here. And how will you integrate this one? Well, you can either, this one could be done by partial fraction decomposition. This could be done by partial fraction decomposition because we have a u here. Yeah. So let's see how we're going to do this by partial fraction decomposition. Or you could look it up in the tables of the integral tables of integration. But let's see, if we call this u, actually, yeah, why don't we call, let's try something. Let's try z squared plus r squared minus 2rz u to equal w. Then minus 2rz du equals dw. Now remember, I'm integrating with respect to u, right? Okay, good. So now what I could do is I could split the integral. into 2, be easier. Or let's just put it together and see what we get if we don't. So we get z minus r times u. Yeah, it's probably better if we split it. So let's split it. So z over z squared plus r squared minus 2rzu to the 3 over 2 minus, can leave the r out, u over z squared plus r squared minus 2 r, yeah, so partial fraction is probably the best way to go, du, right? Okay, so we called, so there's a du here, so we called that w, so then we get, so the first part will become z, and du is just dw divided by negative 2rz, right, over w to the 3/2. Okay, minus r again, du, let's see, well, what's u? U is z squared plus r squared, wait, let's call this yeah, this will need let's just call this alpha, right, to make this a little simpler. This is a number, so let's just call it no, let's call it k. Okay, and let's call 2rz c, so we don't have to keep writing them. Okay, so here we have the integral of u over k plus cu to the 3/2 gu, right? So the first one we're pretty much done with. The first one is easy. You get well, I'll come back to the first one. Let me deal with this. So u, so I'm gonna call now s to equal, or let's not use s, l to equal k plus cu, which means dl equals c du, right? Okay, good. So this becomes minus r integral u is just l minus k over c, and remember those are all constants, and this is 1 over l to the 3 over 2, and du is just dl over c. Okay, so this is very straightforward. So this becomes minus r over, I'm going to bring the constants out, c squared l to the 3/2, right? Integral of l minus k dl, which again is a straightforward integral. Oh wait, I couldn't have taken this out, yeah? This is l over 3/2, and this is l over 3 over 2. Okay, now straightforward. So minus r over c squared. The first one is L to the minus half. So it becomes L to the half times 2, right? Minus K minus 3 halves, add 1, becomes L to the minus half divided by minus half or multiplied by negative 2. So this becomes plus 2. Here we go. And on the first integral, we get 1 over 2. Let me do it in green since it's in green. So 1 over 2rz, right? And by the way, this z crosses out that z, so I don't need a z. So this becomes minus 3 halves, add 1, so minus half and multiply by minus 2. So this 2 cancels that 2. And the final answer will be 1 over r w half. Okay, so putting these two results together, we will get, as a result, plug in everything back into the equation. We will get E equals 1 over 4 pi epsilon. We had here 2 pi r squared times sigma. Two pi r squared times sigma, and then open bracket 1 over z squared, right? We're gonna get zu minus r over r squared plus z squared minus 2rzu. If you remember, our u was cosine theta. And then there's a square root here, and we will evaluate this from minus 1 to 1. And of course, when you do that, you will get, and this is all in the z direction. So when you do that, you will get 1 over 4 pi epsilon, right? 2 pi r squared sigma. 1 over z squared can come out, has nothing to do with this. And if you plug in 1 for u, you will get z minus r over r squared minus 2rz plus z squared minus so this becomes minus z minus r, right, over r squared plus 2rz, because u is minus 1 now, plus z squared square root. Okay, well, fortunately we can factor these two terms. So if we factor these two terms, we get E equals 1 over 4 pi epsilon 2 pi r squared sigma 1 over z squared. This is z minus r over r minus, now here you have to be careful. So you get r minus z squared square root, right? Minus z minus r over r plus z squared square root. Okay, yeah, here you have to be careful a little bit with the negative term, because technically when you cancel the 2, you're gonna get the absolute value of r minus z. You're gonna get the absolute value of r minus z, and here same thing, but this is r plus z, right? and we have 1 over 4 pi epsilon 2 pi r squared sigma over z squared. Okay, now you have to be careful here. If you are outside the sphere or the shell, right? If z is greater than r, that means we are outside the shell. So if z is greater than r outside, yeah, then Ez becomes 1 over 4 pi epsilon 2 pi r squared sigma over z squared. The r minus z, when you remove the absolute value, becomes z minus r. So this is z minus r over z minus r minus plus z plus r over z plus r, right? So this is a 1 and this is a 1. 1 plus 1 is 2. 1 plus 1 is 2. And so we get a 4 altogether. So E, right? So E along the Z. So E along the Z becomes 4 pi r squared sigma over 4 pi epsilon z squared. And what is 4 pi r squared sigma? Yeah, that's the total charge. So that is just Q over 4 pi epsilon z squared. Right, exactly. So that's a point charge electric field. So right. I mean, this Q is it's as if you're seeing this entire surface charge at a point with charge Q. And now let's take the second case. So the second case, when z is less than r, that means you are inside the shell. Well, what do you expect E to be inside a conductor? 0. So let's find out if we're going to get 0, because if we don't, that means something is wrong with our expression. So we get 1 over 4 pi epsilon 2 pi r squared sigma over z squared. Okay, now the absolute value of r minus z becomes if z is less than r, becomes r minus z. So we get z minus r over r minus z, and this is just minus 1, right? Minus, I'm gonna make it a plus and make this z plus r, and the bottom r plus z is just r plus z, or z plus r, which is plus 1. Bingo. Minus 1 plus 1, 0. So E is 0. So that means the derivation of our expression and the integration was correct. So inside, you don't see any electric field inside the shell. Questions on this problem?